Welcome to solverfy.
In this problem, we need to find the wavelength range for the Lyman and the Balmer series, together with the frequency ranges. So we first begin with the Lyman series. So if we consider that this is the ground state of the hydrogen atom and this is the second state, and then we consider an final stage which is the infinite state. Lyman series belongs to all the transitions that have their final state as 1, which is the ground state. So the longest wavelength in this case corresponds to the transition from second state to 1. In this case, delta E, which is 2 to 1, is given as the energy of 2 minus the energy of 1. The corresponding wavelength is given as C over F, or in this case we can say HC over CF. With this, HF is the energy of the photon which is emitted. So it is HC over delta E. Substituting all the values, we can say that En is equal to minus 13.6 over n square EV. So according to the lambda value that we get for 2,1 is 122 nanometers. Similarly, the shortest wavelength would correspond to the maximum energy, and that is when there is a transition from free electron to the ground state. So this is infinity 1. That is simply given by the energy, because the energy of this state is 0 and energy of this state is minus 13.6 EVs. So by doing calculation, we get that this is equal to 91.1 nanometers. Thus, the wavelength range for the Lyman series is 122 minus 91.1, which is equal to roughly 31 nanometers. So this solves our part A. Next, we go to the second part, which is part B. For this, we need to find the frequency range for the Lyman series. Once again, we can directly convert those wavelengths into frequencies. So the frequency range in this case is given as C over the lambda, which is the lambda for one case. In this case, that is infinity to 1 minus C for the lambda of 2, 1. That should be equal to C over 91.1 nanometers minus C over 122 nanometers. And this is effectively equal to 8.2 terahertz, where tera is 10 power 14. Similarly, we need to also solve for the Balmer series. Now, Balmer series is when there is a transition to the first excited state, which is n equal to 2. So if the final state is 2, we have Balmer series. So in this case, the longest wavelength would correspond to a transition from 3 to 2. And thus we can say that the energy is 13.6. So the wavelength 3 2 upon same calculation comes out as 656.3 nanometers. And the shortest wavelength in this case would correspond similarly to infinity to the second state, and that's given as 364.6 nanometers. So now we have a wavelength range delta lambda as equal to 656.3 subtracted by 364.6, which is equal to roughly 292 nanometers, and that's around about 0.292 micrometer. So you see, compared to the Lyman series, which was in terms of 31 nanometers, this is roughly in terms of a micrometer. Similarly, we also need to find out the transition wavelengths. So the delta F for the Palmer series, that is again given by C divided by the lambda. So that is 656.3 nanometers subtracted by again the wavelength for the other frequency for the other wave, and this comes out as 3.7 terahertz.